Welcome back. So, you've made it to part 4 of our deep dive explainer series. Today, we're focusing entirely on scheduling and operations. Think of this as getting to know the two most important roles in the OpenClaw architecture, the traffic controller and the clockmaker. Let's just jump right in. Okay, let's dive into this by looking at a massive architectural problem. Imagine you've got OpenClaw hooked up to WhatsApp, Slack, Telegram, and Discord. Sounds great, right? But what happens when 15 different platforms, or even 15 different users on the same platform, ping your AI at the exact same millisecond? If your system just tries to answer every single one of them all at once in a single memory context, yeah, you get immediate context collapse. The AI gets totally confused, wires cross, and that whole illusion of a personal, seamless assistant, it just shatters completely. To handle this kind of chaotic, simultaneous input, the system absolutely requires a traffic controller, a really rigorous, lane-based command queue to wrangle all that chaos into order. So how exactly does OpenClaw handle that chaos? Well, it's actually pretty brilliant. Picture a whiteboard mapping out these global lanes. On one side, you've got this massive influx of inbound messages coming from literally everywhere. A WhatsApp message here, a quick Telegram ping there, a Slack notification. But, and this is key, they don't just dump into one massive, messy bucket. Oh no. They are carefully, methodically routed into a lane-based concurrency system. The registry acts as our traffic controller. It identifies exactly where the message came from and who sent it. And then it places it into a very specific per-session lane right in the center of the whole operation. Now, you really have to notice the stark difference in how these lanes actually operate. It all comes down to their concurrency limits. Let's look at the session lanes first. They operate with a concurrency of exactly 1. Literally 1. That means individual user sessions queue up single file, and honestly, this is absolutely vital. By processing just one message at a time per user, the system meticulously preserves the conversational context. It actually finishes thinking about your first text before it even starts reading your second. Makes sense, right? But contrast that with the global lanes. The main global lane processes up to 4 tasks at once, and the cron lane? That operates entirely in parallel. So OpenClaw is maintaining strict, single-file order where context matters, while simultaneously running massive throughput for background system tasks. It's the best of both worlds. So what does this actually look like in practice? How does it affect the AI's behavior? This brings us to queue modes. You see, a queue isn't just some passive waiting room. It actively dictates the flow of the conversation. Think of it like a human conversation. The default mode here is called collect. Imagine a friend sends you 5 rapid-fire text messages. You don't reply to each one individually, right? You collect them, let your friend finish their story, and then coalesce all of that into one single reply. That is exactly what OpenClaw does by default. On the flip side, we have interrupt, which, well, is exactly what it sounds like. It completely cuts the AI off right in the middle of a thought to run the newest command. And then you have these highly advanced modes like steer. Steer is super cool because it allows the system to smoothly inject new queued information right at the next tool boundary, and it does it without breaking the AI's current thought process. But, things don't always go perfectly. What happens when things go wrong? Like, what if a user accidentally pastes an entire novel, line by line, and just floods the queue? Well, looking at the configuration parameters, we can see some really clever built-in failsafes. First off, the debounce is set to 1,000 milliseconds. That gives the system a natural 1-second pause before acting on a follow-up. But the real lifesaver is the capacity and drop rules. The queue is capped at 20 messages. If it hits that overflow limit of 20, it doesn't crash. And importantly, it doesn't just blindly delete your data either. Instead, it uses a rule called drop summarize. It actually prompts the AI to compress and summarize the oldest queued messages. This preserves the overarching context of the conversation without totally blowing up the memory window. And as a really nice touch, you can set per-channel overrides, so your Slack queue can behave entirely differently than your Discord queue. All right, so we've mastered the traffic controller. Now it's time to shift gears and meet the clockmaker. This second half of our explainer is all about time and scheduling. Imagine a flow of events starting from the very top. You've got your 3 main trigger sources: a scheduled cron job, a default 30-minute heartbeat timer, or an external webhook. Notice how they all flow downward through the system? Whether it's the cron service or the heartbeat runner, they ultimately do the same thing. They enqueue a system event. That event drops right into the exact same queue we were just talking about, waits its turn, and finally lands at its destination, an agent run. This design is crucial because it ensures that background tasks and active user chats share the exact same robust pipeline. To give developers ultimate control over this clockmaker, the engine provides 3 exact formats for scheduling these background triggers. First up is at. This is a one-shot execution tied to a specific ISO 8601 timestamp. You'd use this when you want the AI to send a reminder exactly at, say, 9 a.m. next Tuesday, one and done. Second is every. This one relies on a fixed millisecond interval, which is absolutely perfect for something like, hey, check my email every hour. And finally, you have the classic cron format. This uses that standard 5-field expression paired with a specific time zone, allowing for highly complex, recurring background schedules. But here is where the architecture gets really smart. When that alarm clock finally rings, where does the background task actually execute? Well, you actually have 2 choices. If you target a main session, the background task actively participates in your ongoing conversation history. So when you open your chat app later, you'll actually see the AI talking to you, continuing the thread. But let's be real, often you don't want all that background noise cluttering up your personal chat. That is exactly where isolated sessions come in. These spin up cleanly in the background, like a totally fresh start. The AI goes off, does its research, completes the scheduled job, and then simply posts a concise summary back to your main chat. It's a fantastic way to keep your interface clean while the system does the heavy lifting behind the scenes. Now, I want to draw your attention to a very specific, kind of nerdy engineering detail about how these schedules are stored and run. The system explicitly relies on recursive setTimeout functions, completely avoiding the standard interval. You might be wondering, okay, why does this matter to me? Well, imagine a background AI task takes 2 minutes to complete, but your interval is set to trigger every single minute. If you used interval, those triggers would just pile up, collide with each other, and eventually, they'd crash your node. It's a mess. By using recursive timeouts instead, the clockmaker ensures that the next countdown literally cannot begin until the previous background task has safely and successfully finished. It is just a brilliant, fail-safe approach to asynchronous time management. And this actually brings us to a really fascinating point about the reality of modern AI development. You will so often hear this romanticized marketing talk about AI agents dreaming or pondering in the background while you sleep. I really want to ground us in technical reality here, pointing directly to the official manual. OpenClaw explicitly states it does not have a dream concept. So what looks like an AI magically deciding to do background work on its own volition is, in reality, a beautifully orchestrated combination of those periodic heartbeats, scheduled cron jobs, external webhooks, and the async queues we just dissected. It's not magic, guys. It's just spectacular engineering. Which leaves us with one final, kind of provocative question. We've seen the traffic controller managing all those chaotic inbound messages. We've seen the clockmaker keeping perfect collision-free time for background tasks. But an AI that only talks to itself on a schedule isn't really all that useful, is it? So if OpenClaw can flawlessly orchestrate all this internal traffic in time, how does it securely break out of its box to extend its reach to the outside world? How does it actually interact with your calendar or your web browser or your local file system? Well, that question leads us perfectly into our next topic. Next up, in Part 5, we are going to explore exactly that, extensibility and the plugin system. We'll unpack exactly how developers bolt entirely new tools, platforms, and capabilities right into this engine. So take a breath, digest all this architecture, and whenever you are ready, I will see you right over in the next explainer.